Assalamualaikum, sir.
यही assignment मिला. So this was your assignment, huh?
Yes, sir. Sir, I have taught in first and second question.
Okay. This was your assignment or?
This was assignment, sir. Same assignment.
Send you this one also.
Sir, I guess question number 1, you didn't teach that concept, I guess.
Yes, it's reflections of partner. That was not your assignment.
Oh, okay.
Question number 2. So does anyone else tried these questions? Ahmed? No.
No, sir.
A small coin is resting on the bottom of a beaker filled with liquid. Okay, this is the coin. A ray of light from the coin travels up to the surface of the liquid and moves along its surface. Okay, how is the light travel? How fast is the light traveling in the liquid? So you need refractive index of the medium. So for refractive index of the medium, you can calculate this angle. This angle of incidence. So this is the angle of, if this is I, then this is I. This is 3, this is 4, and this is hypotenuse. So that will be 3 root over 3 square plus 4 square. 16 plus 9 root over 25, which is equal to 5 centimeter. This is it, 5 centimeter. So you can calculate sin I from here. Sin I is perpendicular upon hypotenuse, so that's 3 by 5. Sin I is 1 by n. So you can write that your n will be 5 by 3. This is the refractive index. So once you have refractive index, you can calculate the speed. So refractive index is speed of light in vacuum divided by the speed of light in medium. So 5 by 3 is speed of light in vacuum, which is 3 into 10 raised power 8, by speed of light in medium, which is v. So you can write v is, it's 3 into 10 raised power 8 divided by 5. So that's 9 by 5. 9 by 5 is 1 point. How much is it? 9 by 5, 1.8 into 10 raised power 8.
Sir,
Yes, Abdul.
sir, how sin I is 1 by n? That is my note.
You can apply Snell's law. This is angle of incidence. So this is your angle of refraction, which is 90 degrees. So let's apply Snell's law here. So when you apply Snell's law here, this is sin I into refractive index of water, which is sin 90, into refractive index of air, which is 1. So you can write that sin I is 1. Okay. See the next question. The frequency of light waves in a material is this and wavelength is this. The refractive index of the material. So I received just 2 assignments, one from Abdullah, another from Malia. See question number 3. So light wave in a material is this, frequency is this, wavelength is this, you need refractive index. So you can write refractive index of a medium as wavelength of light in vacuum divided by the wavelength of light in medium. This is how you can calculate refractive index, wavelength of light in vacuum divided by wavelength of light in medium. So the wavelength of light in medium is given, lambda medium is given. It's 5000 angstrom. But wavelength of light in vacuum is not given. So to calculate wavelength of light in vacuum, you can use this fact that frequency does not change during diffraction. Means frequency of light in vacuum and frequency of light in any medium is same. Frequency does not change during diffraction. So you can say that frequency in any material is, even in vacuum, the frequency is 2 into 10 raised power 14 hertz. Once you have frequency, you can use this fact, speed of light is frequency into wavelength. So from here, you can write that wavelength will be speed of light divided by frequency. Speed of light in vacuum is 3 into 10 raised power 8. Frequency is given as 2 into 10 raised to the power 40. So it comes out to be 1.5 into 10 raised to the power 8 minus 14 is minus 6. That's wavelength. So can you just say that refractive index is speed of light in wavelength in vacuum, which is 1.5 into 10 raised to minus 6 divided by wavelength in medium. Wavelength in medium is 5,000. 5,000 into 10 raised to power minus 10. So this will go up and it will be 1.5 into 10 raised to power 4 by 5,000. So it's 50,000 by 5,000. Gets cancelled out, it's 3. So answer is this. Fourth part, a beam of monochromatic light is refracted from vacuum into a medium of refractive index 1.5. The wavelength of the refracted light will be. So when light travels from one medium to another, its wavelength decreases, right? So wavelength will be small. In diffraction, speed of light changes, also the wavelength changes. So when a light is traveling from one medium to another, then its wavelength is decreasing. Its wavelength is noted down. Written?
Yes, sir.
Yes, Amalia. So that the first question was not a part of your assignment. So they added it by mistake. It's not a part of your assignment. It's not a part of your assignment. Your assignment starts from question number 2, 3, 4, only these. First question is from reflection, so that's not in syllabus now. They place it by mistake. It's okay?
Yes, sir.
Okay, let's start with refraction. So we're doing refraction, just 1 minute. Okay, so up to last class, we have finished for the last topic that we did this apparent depth. After apparent depth, the next topic is TIR, total internal reflection. So see what is total internal reflection. TIR. So we are studying refraction, but now this topic is of reflection, total internal reflection. So see what does total internal reflection means. So what happened when a ray travel from denser to rarer medium? Faisal? When a ray is traveling from denser to rarer, how does it bends? It bends towards the normal or it bends away from the normal? Faisal?
So rarer to denser,
Denser to rarer. Rays moving from denser to rarer medium.
away from the normal.
Yes, it will bend away from the normal. So in TIR, in total internal reflection, what happens is your wave is traveling from a denser to rarer medium. So this is the denser medium and this is rarer medium. When ray travel from denser to rarer medium, it bends away from them. So your angle of refraction is greater than the angle of incidence. In Snell's law, we did that angle of incidence and angle of refraction are directly proportional. Means if you increase angle of incidence, then angle of refraction will also increase. So what happens here is, if you increase this angle of incidence, then this angle of refraction will increase. You keep on increasing this angle of incidence and you make it equal to critical angle. So as soon as your angle of incidence is equal to critical angle, the angle of refraction becomes 90 degrees. So critical angle is that particular angle at which the angle of refraction is 90 degrees. That angle is known as critical angle. So for critical angle, your angle of refraction becomes 90 degrees. This is critical angle. And if you increase your angle of incidence, then critical angle means if your angle of incidence is greater than critical angle, then what happens is your ray will reflect back into the same medium. If you can see that your ray is rotating anti-clockwise, keep on increasing the angle of incidence, the angle of refraction will increase. At a particular angle of incidence, which is known as critical angle, the angle of refraction becomes 90 degrees. But if you increase your angle of incidence, then critical angle, if it is greater than critical angle, then your ray will reflect back into the same medium. It will come back into the same medium. This is known as TIR. And this is reflection. So we call this angle as angle of reflection. This is TIR, total internal reflection. So the phenomena in which ray of light traveling at an angle of incidence greater than the critical angle. So these are the two conditions. One is angle of incidence should be greater than critical angle and ray should travel from denser to rarer medium. It totally reflects back into the same medium. This phenomena is known as TIR. So the necessary conditions for the TIR are: first, ray should travel from denser to rarer. Second condition, angle of incidence should be greater than the critical angle. These are the necessary conditions for TIR. Ray should travel from, yes.
The TIR is like the when the ray will reflect back.
Yeah, ray will reflect back into the same medium. But this reflection is through transparent medium. There's no mirror. There's no reflecting surface. A transparent medium. Light is traveling from glass to air. Instead of going into the air, it's coming back to glass. That's TIR. Note it down. We'll do some calculations. This TIR is the most important. It's one of the most important. Faisal, is it clear what is TIR exactly?
Yes, sir.
That critical angle it reflects back, right?
Critical angle is?
Like the light rays falling on critical angle reflects back.
No, no, no. Light will not reflect at critical angle. The light will graze. See? The light ray is grazing over the surface. It will graze. If it will reflect back if your angle of incidence is greater than critical angle. Okay? TIR occurs at and if angle of incidence is greater than critical angle, not at critical angle. Can I scroll it?
Yes.
written?
No, sir.
Okay, so when I apply Snell's law at point B, this is point B, and let's apply Snell's law.
Okay, scroll down. There's 2 points, 2 points.
Done, sir.
So now I need a relation between this critical angle and this refractive index of the medium. So let's derive a relation. I should write it. See. So if I apply Snell's law here, means at point B. So who will apply Snell's law here? Ahmed, apply Snell's law in the product form. What is refractive index here? ND. And what is angle? C. So what should be the first statement? Ahmed, you are not audible. Your voice is very, very low.
ND into C is
Sin
equal,
C.
sin C is equal to
Yes.
NR into sin R.
Very good. Refractive index of rare medium into sin. So you can write, and how much is R? R is 90 degree.
Yes.
So you can write that your sin C is NR sin 90 is 1 divided by ND. So your sin C is 1 by ND by NR. Or you can write this, I'm taking this NR to the denominator. So I'm writing this because ND by NR is refractive index of denser medium with respect to rare. So this is the formula for critical angle. You can say sin C is 1 by refractive index of denser medium with respect to rare. This is sin C. That's how you calculate critical angle. And remember, refractive index is inversely proportional to the wavelength. So sin C and refractive index are inversely proportional. That will mean that sin C is directly proportional to the wavelength of light. Do it. We'll do few applications of TIR, then we will come to numerics. Maria, what are 2 conditions for TIR that system should follow for TIR? Yes, Amalia, what are the 2 conditions that system should follow for TIR?
Sir, I don't know. I didn't complete writing.
Okay, you didn't complete writing. You didn't wrote this thing?
No, sir.
Okay, please first note it down.
Can you do me a favor? There's this black sweater at the back.
Which one? Sorry. Yes, noted. Amalia, can I scroll it further?
Yes, sir. Yes, sir. I'm completed.
So see, applications of TIR. The first application is sparkling of diamond. Diamond sparkles due to TIRs. So what happened is the critical angle for diamond is 24.4 degrees. So let's say this is diamond. When a light ray enters into the diamond, it undergoes TIR. So when a light ray undergoes TIR, what will happen with the light ray? It will move out of the diamond, it will remain inside.
It will remain inside.
It will remain inside. So the light ray will remain inside. Then it again undergo TIR. Again, it will remain inside. Then it will again undergo TIR. It will remain inside. So this light ray will get trapped inside the diamond. It can't move outside diamond. That's why it seems sparkling. So the sparkling of diamond is due to the TIR, the first application. Note it down. So in diamond crystal, light suffers multiple TIR. That's why it sparkles. And that's the high density of diamond, due to which critical angle is comparatively small, 24.4. As compared to normal glass, the critical angle of diamond is very small. For a normal glass, critical angle is around 45 degrees. But for diamond, it's just 24.4 degrees. Written? Can I scroll it further?
Yes, sir.
Then the next application is Mirage. It's a type of optical illusion. I think Mirage should be very common in deserts, huh? In Bahrain, like in Middle Eastern countries, Mirage is very common, optical illusion. So you must have observed this Mirage. In Mirage, what happens is, let's say, not exactly in desert, but even on highway, if you are driving in summers on highway, it seems like there is some water on the road. Have you observed it somewhere? When you're driving on a highway on a very high temperature, like
Yes, sir.
when the temperature is around 40 to 45 degree, you will observe there is some, it seems like there's some water on the road, but when you go near that spot, there is no water. So that optical illusion is Mirage. It's a shimmering bond of water. It happens on a road, it happens in desert also. That's an optical illusion. So what happens in Mirage is, say, let's say this is a tree. These are air columns. As you move away from the ground, the temperature of the air decreases. So that's a cold air, which is a denser air. This is hot air, which is a very rare air. As you move from the ground to an altitude, the density of the air increases. As density of the air increases, the air becomes denser, the refractive index increases. Hot air is rarer and the cold air is denser. So let's say this is a tree. You are traveling somewhere here. This is you in a car. And this is a tree. The rays are coming from the tree. So rays are coming from denser to rarer medium. The first condition of TIR is getting fulfilled. Rays are traveling from denser to rarer medium. So rays are coming from denser to rarer, denser to rarer, denser to rarer. At some point, this angle of incidence becomes greater than critical angle. So what happens is ray will reflect back into the same medium. If someone is standing here, or this ray can even travel here, if you are looking, if these rays are going to your eyes, then you will observe that the image of the tree, you will observe that image of tree is on the ground. You'll observe this image on the ground. So, and when you observe that image of a tree is on the ground, it seems like there is some water in which its reflection is there. Your brain take it in this way. You're traveling on a highway, you see the image of a tree on the ground. So your brain take it in this way, that there is some water on the ground on which the reflection of the trees is there. So it seemed like there is some water on the ground. This optical illusion is known as mirage. So mirage happens at a very, very high temperature. Is it clear, Mirage?
Yes, sir, it's clear.
Please note it down.
Yes, Leonard. What is that? Like a coal?
Which one?
The second sentence, second line. Like a coal.
Koltar, the road of Koltar. Koltar. That black sticky material used to make. Written?
Yes, sir.
Draw this ray diagram. So for the time being, just leave this ray. So in TIR, in Mirage, you're basically getting image of tree on the ground, which seems like it's just some water.
Done, sir.
There is one more optical illusion, which is known as blooming happens in extremely cold climate, like in North Poles, Antarctica, you will observe blooming. Blooming is just inverse of mirage. Blooming, what happens is image of an object on the ground is observed in the sky. Like image of a ship appears in the sky. It's again due to TIR, same TIR. But now the TIR is in the opposite directions. So there's an object on the ground, its rays are going in this way. So when you look at the image, it seems to be in sky. So again, optical illusion, just reverse of blooming. Blooming, that mirage happens in very cold climate, while looming is extreme. Sorry, mirage is at very hot climate. For mirage, temperature should be very high. For looming, temperature should be very extreme cold climate.
Sir, looming is like in North Pole, South Pole.
Sorry, which one?
Looming will be in North Pole and South Pole.
Yeah, North Pole and South.
Okay, sir.
So sometimes it seems like the ship is flying. So that's the image of the ship is in the sky. That's the way mirage makes the image of sky or the tree on the ground. In looming, it happens just the reverse. Like it's image of an object on the ground obtained in the sky.
Done, sir.
Everyone, Faisal, Amalia, written.
Yes, sir.
See next, totally reflecting prism. So totally reflecting prism is a right angled isosceles prism. See, usually prisms refract light rays. Prism are transparent material. They are used for refraction. But you can use prism to reflect light ray also. So if you have a right angled prism, like prism having 45-degree, 90-degree, and 45-degree angle, it's known as a reflecting prism. This prism can reflect your light rays. So in a prism, whenever light rays enters in a prism, the angle of incidence is 45-degree. The critical angle for prism is 42-degree. So this is angle of incidence and this is critical angle. So whenever light ray enters in a prism, it undergoes TIR, total internal reflection. So using a prism, you can deviate light ray in two ways. You can either deviate a light ray by 180-degree or you can deviate a light ray by 90-degree. Do it again. So in a prism, you can deviate your light ray by 90-degree or you can deviate it by 180-degree. See how will you deviate it by 90-degree. So see, this is your prism. So that's your triangle. So this is a right angle triangle. This angle is 90-degree. This is 45-degree. This is also 45-degree. I incident a light ray here normally. See, the light ray which is going normally will not undergo any refraction. Refraction occurs in only those rays which are coming obliquely at some angle. But ray which is going at 90-degree will not refract. There won't be any refraction in this light. This is normal. This is normal. So Faisal, can you decide how much is this angle? This one. This is 45. This is 90, Faisal. How much is this angle?
So 45.
45. And this hole is 90-degree. This is normal. Then how much is this angle?
45.
45. For glass, critical angle is 42-degree. So what will happen here? Will this ray comes out of the glass or it will remain within the glass? Yes, sir. This is your angle of incidence, right? 42, 45-degree. And critical angle is 42-degree. So what will happen with this ray? This will come out of the glass or it will remain within the glass?
So it will remain in glass.
It will remain in glass. It will undergo TIR. So it will go in this way. This will undergo TIR. Angle of incidence is greater than critical angle. And when this light ray incident normally on this phase, then it will go straight without any reflection. It will go straight. It will pass straight. So this is how you can deviate a light ray by 90 degrees. If you take another ray, it goes here in this way. Then it goes here in this way. So if you take an object, I call this as A and this is B. So you're getting the image of the object in this way. This is A and this is B. So your object gets deviated by 90 degree if it is passing through a prism this way. So in a prism, you can deviate your light ray by 90 degree. Similarly, in a prism, you can also deviate your light ray by 180 degree. Is it clear how it is deviating by 90 degree?
Yes,
It's
sir.
TIR, just one single TIR is, and you can also do image formation here. This object which was erect get tilted by 90 degree. Note it down. Then we'll see how can we like deviate a light ray by 180 degree using a prism. Now it will undergo 2 TIR.
Sir, the objects, I mean, the image gets inverted.
Image is not exactly inverted. It's just deviate by 90 degree. Like if you look at this pen through that type of prism, then its image will look like this. Fixed by 90 degree.
So if it deviates by 180, then
Yeah, then it will be.
okay, sir.
Can I scroll it now?
1 second. Sir. And done, sir.
Everyone have written up to there?
Yes.
Yes, sir.
Or draw this ray diagram. Then we'll see how can we deviate a light ray by 180 degree using a prism. Yes, can I scroll it further?
Yes, sir.
So see, how will you deviate your ray by 180 degree? So let me run this first. Same prism can be used to deviate your light ray by 180 degrees. See, this is your prism. This is 90 degree angle. This is 45 degree. Now this is also 45 degree. So you incident a light ray normally on this face. So this is going normally, so it won't refract. This angle is 90 degree. This is 45 degree. Then how much is this angle, Ahmed? Yes, Ahmed. How much is this angle?
45 degree.
45 degree. If this is 45 degree, then this is again 45 degree, but this whole is 90 degree.
Yes, sir.
So is this angle greater than critical angle, Ahmed?
No, sir.
How much is critical angle for glass? Its critical angle is 42 degree. So is it greater than critical angle or less than critical angle?
I said it's greater.
It's greater. So what will happen? The ray will come out of the prism or it will remain
No,
inside
sir,
the
it will internal reflection.
Yeah, so it will remain inside. Then again for this phase, it will again undergo TIR. This angle is again 45 degree. This is again 45 degree by the same geometry. So it will again undergo TIR. So see, the ray was going to the right, and when it is emerging from the prism, it's going to the left. So it deviates by 180 degree. If you take an object here, if you take one object here, call this as point A, you call this as point B, this is your object. So this ray is going straight, reflect here, and come back. So this is it. This is A prime, this is B prime, this is the image. So a prism can deviate a light ray by 180 degree. Just deviate. The image of the object get flipped by 180 degree. So this is deviation of ray by 180 degree. This is it. So if you're taking an object, then image get inverted by 180 degree. You get an inverted image. Do it.
Done, sir.
Everyone written?
Yes, sir.
Now the next is optical fiber. Before optical fiber, let's discuss the normal copper fiber. So everyone have used those wired telephones. For mobile phone, they're wired telephones. In a wired telephone, how does your sound travels? Like you have two telephone, one is transmitter, another is receiver, and they are connected through a wire. How does sound travel in a wire? It
Through
travels. It travels in the form of sound waves only, or in the form of something else?
Electricity.
Electricity, right? So in a telephone, what happens is that telephone converts your voice signal into electrical signal, and then that electrical signals travels through the wire. That's why in wired telephone, electrical wires were used. But there is one issue with the electrical signal. The wire have some finite resistance. So when your signal travels in the form of current, basically, your voice signal is traveling in the form of current. Due to resistance, your current decreases, your voice signal decreases. There is loss in the strength of your audio signal and anything. So in normal telephones, the copper wire was used, but the issue with the copper wire is when your sound signal travels through that copper wire in the form of electrical signal, due to resistance, your signal get lost. So you need something where loss is minimum. We can't completely make the loss zero, but we can decrease the loss. And that is optical fiber. What happens in an optical fiber is, in an optical fiber, this optical fiber convert your signals into optical signals. Like it convert your signals in terms of light. And then that light travels through the optical fiber through TIR. The best thing about TIR is there is no loss in intensity. If there is TIR, that means there is no loss of intensity in TIR. 100% of energy is getting TIR, totally internally reflected. In refraction, there is never 100% refraction. Even if you take a transparent surface, that will reflect some part of it. There is never 100% reflection. Even if you are taking a mirror, that mirror is transmitting some part of the light. But TIR is 100%. 100% of rays having angle of incidence greater than the critical angle will reflect back into the same medium. So there is no loss, practically there is no loss of intensity in TIR. That's why in optical fiber TR is used, TIR is used. So what we do is we convert our signals, the message signal into optical signals, light. And that light travels through the optical fiber in the form of multiple TIR. Optical fiber is something very basic thing. There is one coating, one core, which have high density, high refractive index. Then there is another coating which have comparative low refractive index. So light rays are coming from denser to rarer medium. They will undergo TIR, and through multiple TIR, the signal travels. Usually, in internet fibers, like these fiber lines, the internet fiber. What is that fiber? That is an optical fiber. And how does your signal travels in the optical fiber? It travels through multiple TIR. So that's your homework. You will write few 4 to 5 lines about it from the NCERT. Is it clear? What is optical fiber and how it works?
Yes,
Yes,
sir.
sir.
Just a story. Fiber internet, fiber internet, the speed of internet is very high. The quality of internet is very high. What happens there is that fiber is optical fiber that is transmitting your internet signal in the form of this wave TIR. The loss of intensity is minimal.
So what's the homework?
This optical fiber, short note optical fiber. This is very important.
Okay, sir.
Can I scroll it further?
Yes, sir.
Oh, sorry. Solution. Do it. Do this numerical. The straight formula based thing. The rest of the numericals will use other steps, but this is a formula based. You need critical angle of incidence. Just get the value of refractive index of denser with respect to rarer. 1 by that refractive index is sin c. So can I scroll it? Answer. What is the answer?
Just wait.
Write your answer in chat. Just write the value of sin c. I need just sin c. Okay. Noor is correct. Abdullah is correct. Ahmed, you have to inverse it. Huh? That's not sin c. This is what you have calculated is 1 by sin c. Amalia, Faisal, your answers. Yes, it's correct now. Faisal and Amalia. No, Faisal, not 1. See, sin c is 1 by refractive index of density with respect to rarer. So refractive index of denser with respect to rarer is refractive index of denser medium divided by the refractive index of rarer medium. Denser is glass, which is 3 by 2. Rarer is water, which is 4 by 3. This 3 will come to numerator, so it will be 9 by 8.
Sir, I got 9 by 8.
So
Then I
9,
divided it.
9 by 8 is NDR, but your science C is not 9 NDR, it's 1 by NDR. So you have to inverse it. Okay, 8 by 9. That's why I'm saying, So refractive index is correct. 1.1 is denser with respect to rarer. That's correct, but your science C is not NDR, it's 1 by NDR. So you see sine inverse 8 by 9.
And then so
Write this question. Write down this question. It's a bit lengthy, but write it. And please, I'm sharing by tomorrow evening. We'll share 3 to 4 questions based on TIR. So do the assignment and submit it by Thursday. Try to submit it before Thursday. Note it down. Yeah, is it clear? Written?
we have to draw the diagram.
Yes, yes, yes. The diagram is a part of it. See, you're supposed to calculate the value of this angle of incidence at which the ray undergoes TIR over this point. You have to calculate the angle of incidence for which the ray undergoes TIR at this point. Okay, almost everyone is gone. Time is almost over. We'll do this in the next class, man. We'll do this numerical in the next class. So TIR is over. The next class will start with this spherical diffracting surface. Thursday will start with spherical diffracting surface. Okay.
Okay, sir.
Thank you, sir.
Just drop it.
Thank you, sir.